Welcome to part 3 in this series of rational functions. In this video, and any subsequent videos, we're going to use the information that we discussed in parts 1 and 2 and create the graphs of rational functions. So if you missed any of that information, such as horizontal asymptotes or slant asymptotes, vertical asymptotes, or any of the points of discontinuity, check out parts 1 and 2. And I go over all that information in more detail. So as you can see on the screen, I've got my strategy for graphing rational functions. And these are just my steps for graphing rational functions. This is how I like to approach it. This is kind of how I like to attack it. Other people may have their own way of doing it. This is just how I like to do it. So what I'm going to do is I'm going to go through this step by step and go through the entire process and put all the pieces that we learned, as I mentioned, all the pieces that we did in the first 2 videos to use in this video. So if you can see the first step, the first thing is we're going to determine if there are any horizontal asymptotes or slant asymptotes. And I covered that in the last video. So that was in video number 2. All right, so the next thing we're going to do is, in step 2, is we're going to factor the numerator and the denominator. And if you recall from my first 2 videos, I was hopping, big time on factoring. And that's really how you have to go about attacking these functions when you're graphing them. You really need to make sure everything is factored completely. Then what we're going to do is we're going to look for vertical asymptotes, as you can see right here, and then holes, and then the x and y-intercepts. So for vertical asymptotes, I really covered those in the first video in this series, as well as the general graph shape, and I also covered domain. The holes in the graph, as you can see right here, I covered that in the last video. And the next thing in my list we're going to be talking about is the y-intercept and then the x-intercepts. I'm going to wind up covering those in this video, so that's going to be in video 3. So I've got those highlighted from which videos they came from. All right, so we're going to begin the process of graphing these functions. And just before I do that, I just want to show you one quick thing about the general behavior of these functions. So when I actually get into the mechanics of it, it'll make a little more sense. So what I'm going to do is I'm just going to create just a general function here. So let's say I had a vertical asymptote right here at x equals 2. And I had a horizontal asymptote right here at y equals 3. All right? Let's change the color a little bit. Let's create a y-intercept at 0, 4, and let's create an x-intercept at 3, 0. So the general behavior of these graphs, now this is the general behavior. This is not in every case to keep in mind, all right? So what's going to happen is if I look at this rectangle right here in between the horizontal and this vertical, just this piece right here, what will happen is the graph of the rational function will actually go down towards the vertical asymptote, all right? So it's going to go down that way, and it's going to go up towards the horizontal asymptote like that. It's kind of going to use the asymptotes as almost like a little guide, all right? So it's going to use that as a little border there, look, a little guide. All right, and then the same thing is going to happen if we're up in this rectangle up here. It's going to wind up going up towards the horizontal or the vertical asymptote this way, and it's going to go down towards in negative infinity direction. It's going to go towards the horizontal asymptote that way. And that'll be the general behavior of these functions. Now again, that's not in every case. So one thing to keep in mind, if I just erase this part here, a rational function will never ever do this. It'll never get close to a vertical asymptote and cross it, okay? Because what would happen is if it was able to do that, that means if it crossed it, there has to be a point on the asymptote where it was actually equal to that. And we know that these graphs can never equal any value on that vertical asymptote because that would create an undefined situation. That would be like at this place on the line here at x equals 2. At this x value right here at 2, that would have been a place, if you watched video 1, that would have been a value where the denominator would have been made equal to 0. So 2 would have created a situation where the denominator would have been 0. So any vertical asymptote would have created an undefined situation, so there is no place on that asymptote where the function could equal that. But what could happen, if I go the other way now, if I just recreated this graph, if we did it the right way and approached the vertical asymptote, so what could happen if we went this way? The graphs could go through the horizontal asymptote, and it would be fine to do that. Sometimes these graphs do approach the horizontal asymptote and actually do go through it, and then they kind of go back towards it. If you saw what happened over here, it kind of went through it, and then it goes down, and it'll kind of, if it goes off to negative infinity, it'll kind of go back towards the horizontal asymptote. These graphs can do that. So that's the general behavior of the graph. So what I'm going to do now is I'm going to take, if we go back up to my steps here, I'm going to take each step one by one, and I'm going to separate the video into little sections, and we're going to just complete this graph. I have the function down here. I have f of x equals x squared minus x minus 6 divided by x minus 1 over x plus 2, and we're just going to go through every step one by one. All right, so let's look at the first step. First step says determine if there are any horizontal asymptotes or slant asymptotes, and then sketch. All right, so what I'm going to do is I'm going to write it out for step 1. So we're going to determine, is it going to be a horizontal or a slant asymptote? And if you remember from the last video, what you're doing is you're looking for the degree of the denominator and the degree of the numerator, and you're comparing them. So if I look at the degree of the numerator is 2, all right? And the degree of the denominator, and this is, the denominator has already been factored for us. So really I have x to the first and x to the first. And if you were to multiply all these out, if you would multiply these factors out, you would realize that the degree of the denominator would also be 2. All right? So that would mean that we would have equal degrees in the denominator and the numerator. So what that means is if the degrees are equal, what we need to do is we need to take the lead coefficient. So the lead coefficient of the numerator would be 1. So you take the lead coefficient of the numerator, and then you would take the lead coefficient of the denominator. Now the lead coefficient in front of both x's is 1. So again, if you multiplied everything out, you would have 1 times 1 is 1. So your asymptote would be a horizontal asymptote at y equals 1. If the degrees are equal, you take the lead coefficient. This is what I went over in video number 2. You take the lead coefficient of the numerator and the lead coefficient of the denominator, and it's going to create a horizontal asymptote, y equals 1. All right. So what I like to do is I like to pencil them in as I find them instead of doing them all at once. So what we're going to do is I'm going to pencil in the horizontal asymptote at y equals 1. And we'll have all that. Now that's going to be my first guideline. Then we're going to go to step 2. If I scroll back up, and step 2, as you can see it, is going to be factor. So we're going to factor the numerator and denominator, and if possible, you can see it right here, we're going to cancel any common factors. All right, so let's go back to my function. Let's clean this up just a little bit so we can see this. All right, so step 2, I'm going to factor now. So here's my function. We're going to have f of x equals. Now the denominator is always already factored, so we can just put that back. So it's x minus 1 times x plus 2. And the numerator, see, that's going to factor into x minus 3 times x plus 2. All right? And then it said, if you remember what it said above, it said cancel any common factors. So what I need to do is I need to check and see if we have any common factors here. That's the place where we're going to find any holes or points of discontinuity in the graph. So let's see, we have our function. So now we're over here, and we can clearly see that we're going to cancel this factor of x plus 2. So what that means, when I cancel any factors, that does mean we're going to create a hole. All right? So I'm going to put just a little asterisk over here that we have a hole. I'm going to come back to the holes in step 3. So I'm going to rewrite the function. So we have the reduced function now. F of x equals x minus 3 over x minus 1. So now going forward, we're going to work through the rest of the steps and just use the reduced function. So that'll help us a lot, and that'll make the work a little bit better. I'm just going to scroll back up to the next step. So in the next part of the video, where we're headed is step 3, and we're going to wind up doing those. Step 3, as you can see, is like the big, this is the heavy lifting step. So we're going to find the vertical asymptotes, the holes, and the x and y intercepts. All right, we'll be right back. All right, so now we're going to find the vertical asymptotes. And if you remember from video 1, the vertical asymptotes are created from all the factors in the denominator when they're set equal to 0. So any factor that's left in the denominator, so if I look at my function here, and what I have, remember we're always working on the reduced function, so we're right here in this part. If I look at the denominator, any factor that's remaining after we canceled, so I left the original factored function up there. So this is what we had originally when we canceled the x plus 2's. So we knew the x plus 2's are going to create a hole. We're going to get to that in a little bit. But this x minus 1, it's in the denominator. What we have to do is we're going to wind up setting what's in the denominator equal to 0, because this is what's going to create our vertical asymptote. So if we solve for x here, we're going to get a vertical asymptote at x equals 1. So I'm going to put that on the graph. That's going to be our next guideline, our next piece. So if we do a vertical line here, we're going to have a vertical asymptote. And this is kind of set up like I did at the intro here. We have a horizontal asymptote, we have our vertical asymptote, and those are going to be our guidelines. All right, so we took care of that, right? And now we're going to go to the next part, and if we scroll up for step 3b, right here, it says determine any holes in the graph, and we've already identified that. We said from earlier, we said that any factor that was canceled in the numerator and the denominator, that's going to create a hole. So we have a hole, and what creates the hole is going to be this factor x plus 2. So if you remember from video 2, what you do is you take your canceled factor, x plus 2, and all you do is you set that equal to 0. And now we're just going to solve that. So we're going to have x equals negative 2. All right. And remember, the hole is just a placeholder. So we need, it's a placeholder on the graph. And on the graph, it needs an x and y coordinate. So this is going to be our x coordinate. And to find the y coordinate, all we're going to do is take that x value and plug it in for x all the way through the function. All right. So to find the y coordinate, so we can actually plot the hole, it's actually going to be f of negative 2. And this is going to be negative 2 minus 3 over negative 2 minus 1. So this is going to give us negative 5 over negative 3, which will give us a 5/3. So we actually have a hole at the place, negative 2, and then 5/3. All right, so I'm just going to magnify this a little bit because that's going to be a little tough to read. So I'm just going to blow that up a little bit. So we have a hole there, and I'm going to plot that hole at negative 2, and then 1, so then we have 1 2/3. So it's going to be negative 2, and it's going to be, it's going to be a little tough to get that exact. So it's going to be kind of like right there. There's a hole there. So we're moving our way through the steps. We've taken care of part 3 is a lot. There's a lot of little pieces in part 3, but we've done the vertical asymptote and the hole. And now the next part is we're going to take a look at and find the y-intercept and then the x-intercepts. And then we'll get an actual, a better picture of the graph, just plotting some additional points in step 4, and then we'll just do the sketch in step 5. So I'll be right back with parts 3C and 3D as we find the x and y intercepts. All right, so now we're still in step 3. We're working through parts 3C and 3D, as you can see. And we just found the hole in the graph. And as you can see over here, if I just highlight this a little bit, we're on this part over here. We just did the hole. So that was the factors which the holes are created, values of x which make the numerator and the denominator 0. They're basically canceled factors. Again, I went over all that in video number 2. What we're going to do now is we're going to concentrate on the x and y intercepts, and you can see here the step for the y-intercept, which is the same for any function. If we're finding the y-intercepts, all we're going to do is set the x value to 0. So we're going to plug a 0 for substitute a 0 in for x, and then determine what the y-intercept would be. And then for the x-intercept, we're just going to reverse it. What we're going to do is we're going to substitute a 0 in for y, and then we're just going to set the numerator equal to 0 and solve. All right, so let's do that. Let's take care of the next couple of steps here. All right, so we're going to do 3C. So this is part 3C, and this is the y-intercept. So to do the y-intercept, what you're going to do is you're going to substitute a 0 in for x, which is standard. For any function, you want to find the y-intercept. So if I do f of 0, we're going to have 0 minus 3 over 0 minus 1. So this is going to give us negative 3 over negative 1. So that would give us a 3. So my y-intercept would be at 0, 3. All right, so there's my y-intercept, and I'm going to put that on the graph. We'll sketch that. So 0, 3 is going to be right here. I'm going to use that. And then the next part is, the last part of step 3, is we're going to find the x-intercept. And again, just scroll back up quickly. The x-intercepts, what we're going to do is you're only going to set, and again, you're going to work on your reduced function. You're only going to set your numerator equal to 0. All right? So here is my reduced function. We're always working off the reduced function after we've canceled any factors. So all we need to do to find the x-intercept is just use the numerator. The denominator was, if we look at the denominator here, it's x minus 1. The denominator was used to find the vertical asymptotes. Now the numerator is going to be used to find the x-intercepts. If we do the x-intercepts, so what you do is you're going to set your numerator. So you're going to have your numerator equal to 0. So all we need is x minus 3. So we're going to have x minus 3 equals 0, and then you just solve that. So my x-intercept is going to be 3, 0. So I'm going to put that on the graph as well. So let's change the color, and we'll have 3, 0. So now we have a picture, and if you're familiar with these graphs, you can kind of see how these are going to go. All right, so remember from the beginning, I said, this graph is, if you see your y-intercept is right here, this graph is probably going to wind up going up towards this vertical asymptote, going up to positive infinity, and it's going to wind up going down to this horizontal asymptote. There's the hole. So it's going to pass through that, and it's going to go down this way. And then in the other direction, it's going to wind up going down to negative infinity this way towards the vertical asymptote, and then it'll wind up approaching the horizontal asymptote this way. But we're gonna figure that out, a little more exactly in step 4, where we create some test points and some test regions and actually get a better sketch. Okay, so I'll be right back with step 4, and we'll get a better picture of how this graph is going to look. All right, welcome to step 4, and this is really a combo step. So this is actually going to be steps 4 and 5, And this is where we're going to determine some test regions and then some test points and figure out, where the graph is either above the x-axis or below the x-axis. And then we're just going to connect the points with a smooth curve. So that's really what we're going to do in this part. This is where everything's going to come together. And as you can see here, this is the example that we've been working on. And on the graph, we have everything that we've done so far. We have our x and y intercepts. We have our vertical asymptote, a horizontal asymptote, and we have the hole that we created. And before I get into the curve here for the actual example, what I did was I just created a little demo graph, and I just wanted to show you how the test regions work. So basically what we're going to do is we're going to use the x-axis to create our test regions. And you can see what I have is, so the test regions are going to be created on the x-axis, as I mentioned. So really we're just dealing with the x-axis. That's all we're concerned about. And the test regions are created on the x-axis by vertical asymptotes and x-intercepts. So I don't really care anything about horizontal asymptotes as far as the test regions go. Here's how this works. So if I use my pointer here, whenever we're reading a graph, we're reading a graph from left to right. All right? If I'm starting our graph here, our test region, your first test region, is always going to be, as you can see it down here, your first test region is always going to start with negative infinity. All right, your first test region will always start with negative infinity. So what you're going to do is, if you kind of imagine this as, like a little road here, we start at negative infinity, and you can see I have my x-axis, the complete x-axis is broken up into different sections with different colors here. So the reason I did that is, what you do is you continue along your x-axis until you hit, and you can see it what I have here, you either stop when you hit a vertical asymptote or stop when you hit an x-intercept. So when I did this, I started at negative infinity and I was continuing along the x-axis and I stopped right here. Because at this point over here, or this vertical asymptote, x equals a, that's where we're going to create our first test region. So as you can see down at the bottom here, I have region 1, and that region will be from negative infinity to this value a. So we went from negative infinity to the asymptote, and then that created the first test region. And then what you do is you continue along your x-axis. You have to complete the full x-axis. So you start the next test region. So this is going to be region 2. You'll start the next test region where the previous test region ended. So we would pick up again at A, and then you can see in the green area, we're going to continue until I hit again either an x-intercept or another vertical asymptote. So you can see I have to stop right here at this point, b comma 0, because that's an x-intercept. So that would create the second test region. So you see I have the first test region up here, and that was in the yellow area. That was from negative infinity to my vertical asymptote. And then we had the second test region, so that's in the green area. So that went from, we started at A and it went over to B, the x-intercept. And then what we're going to do is we're going to continue. We're going to start the third test region. So we start the third test region where the second test region ended. So we start at B, and then we continue it all the way until we hit either another x-intercept, another vertical asymptote, or if we continue it on to positive infinity. You can see this graph has neither another x-intercept or a vertical asymptote. So this one is just going to continue on to positive infinity, and that's where we're going to end the test region. So we have 3 test regions on this graph. So essentially, what does that mean? What we're going to do in this test region, and the third test region again is in that light blue area, what does that mean for us as far as our graph is concerned? So the test regions are going to determine whether all the points, if we went back to region 1, so again, region 1 is just up until with that vertical asymptote, from negative infinity to that vertical asymptote. So what the test regions are going to tell us is whether the graph will be either above the x-axis up here, or it's going to be below the x-axis down here. So for instance, if when we do our test point and we determine that this point is, let's say, right up here, we know that every point in this test region from negative infinity all the way to that vertical asymptote has to be above the x-axis. If one point is above the x-axis, then every point is going to be above the x-axis in that region. So we can draw our sketch and feel pretty confident that every point in that region would be above the x-axis. So it would go from, if we assume that the horizontal asymptote here is y equals 0, this graph would be in this region here, the yellow region, it would go up to the vertical asymptote and kind of curve down towards the horizontal asymptote. Now, if we were in the second region, the green region, and then we found that one of the points was, let's say, down here, so this point is below the x-axis, it's in this region here, then we can say that if one point is below the x-axis, we can say that every other point is going to be below the x-axis in that region. So from the vertical asymptote to that point, and it's going to wind up going down and kind of curving down towards the vertical asymptote that way. So everything in the green region is going to go downwards towards the vertical asymptote. And then the third region, the light blue region off to positive infinity, if we found that since we have an x-intercept, all the points in that region, and we'll test that to prove that, all the points in that region are actually going to be above the x-axis. If we found, one point was above the x-axis, then all of the points would be above the x-axis. So everything in the third region from this x-intercept off to positive infinity would actually be above, and then the graph would, continue out that way. So that's kind of how the test regions work, all right? They're determined by the x-intercepts and the vertical asymptotes. So now what we're going to do is we're going to do this for real with our actual example. So our first test region that we're going to create is, now if we examine the x-axis, again, so if I do this here would be negative infinity, and if I just scroll over a little bit, we would have positive infinity over here. So we would continue, so if I highlight this, let me highlight it a little bit better. So we're going to, start our journey from negative infinity, and we're going to stop when we hit an x-intercept or a vertical asymptote. So right there we stop, bam, we stopped at 1. So our first test region, so test region number 1, so these are going to be our test regions, would be from negative infinity. So this is going to be from negative infinity to 1. All right. So then we're going to, let's just change the color here. So let's change the color, and now we're going to continue. The next test region is going to be from 1, and we're going to stop at 3 because we have an x-intercept. So the next test region, so test region number 2, is going to go, remember, test region 2 starts where the first one leaves off, and we're going to continue that up until that x-intercept at 3. And you can see it right there. All right. And then the third test region, because we have another section that we have to continue on to, is we have to wind up going on to positive infinity. So this one's going to wind up being 3 to positive infinity. So the third test region, just move it up just a little bit. This one is going to start at 3, and then it's just going to go to positive infinity. All right. So that's just how that's going to work. And then all we're going to do is just take x values in these specific regions. So any place on the x-axis, any x value that's in this region, so we could take any x value all the way through here, all right? And we already have a couple. If you see, we already have 1 at 0, right? So we know at 0 it's 3, and then we already accounted for negative 2. We have the whole there. So why don't we kind of focus in on negative 3? Let's just see what that tells me. It's kind of already telling me now, I already kind of know that from everywhere from negative infinity to that vertical asymptote, these 2 points or these 2 identifiers were above the x-axis, and they're actually above the horizontal asymptote, we already know that everything else in that region has to be above the x-axis and most likely above the horizontal asymptote, but we're just going to try another one. So I'm going to pick x equals -3, just as another one, and then we'll just have that one more valid test. So we'll have f, and remember our reduced rational function, it was f of x equals x minus 3 over x minus 1. That was the reduced rational function. So let's substitute the -3 in, and we'll see what we get. So we're going to have f of -3 equals -3 minus 3 over -3 minus 1. So this is going to give me -6 over -4, and this is going to give me a positive 3/2. So at the point -3, we have a y value or an f of x value of 3/2. So I'm just going to sketch that, and again, here's my point here. Let's just be consistent. We have this point, and we can feel pretty confident, again, as we already, pretty much determined that every point from -infinity to the vertical asymptote is going to be above the x-axis and then above the horizontal asymptote. And in the last section in this video, I'm going to show you algebraically how you determine whether the graph will actually cross the horizontal asymptote or not. So this graph is going to wind up going up towards the vertical asymptote. All right, it's going to wind up going up this way, and it's going to get really, really close to the horizontal asymptote in that region. Now what we're going to do is we're going to figure out what's the behavior of the graph from the vertical asymptote to the x-intercept, and we just need to pick an x value. And you can pick as many points as you want. You can pick as many x values as you want to do the tests. You really only need one to determine whether the graph is going to be above or below the x-axis. So I'm going to use x equals 2. I'm going to scroll this up just a little bit. So we're going to do x equals 2. And again, we're using f of x equals x minus 3 over x minus 1. So we're going to substitute a 2 in. So we have f of 2 equals 2 minus 3 over 2 minus 1. And this is going to give us -1 over 1. So this will be -1. So at the x value 2, we're going to get a value of -1. So if we come over to our graph, and so we have 2, -1. So again, that tells me from everywhere from the vertical asymptote to the x-intercept, every point in that green region is going to be below the x-axis. So we know the behavior of how these graphs, how they work. It's going to go this way. It's going to wind up going down towards the vertical asymptote. Remember, it cannot cross the vertical asymptote. All right? And then we just have one more test region to work on. So we can pretty much figure out what's going to happen here. It's going to wind up going up this way, but let's just do a test and make sure of that. So let's do the point from 3 to infinity. So I'm going to use the point, I'm just going to do x equals 4. And we're going to substitute it in. So we're going to have f of 4 equals 4 minus 3 over 4 minus 1. Because again, we're using the reduced rational function. So that is going to give us a value of 1/3. So we have the point 4, 1/3. And then we know 1/3 is positive, so that's above the x-axis. So that pretty much behaved exactly the way we thought it would. So we have this point here, 4, 1/3. Oh, if I change it to an actual writing instrument, there we go. So, the graph pretty much behaved exactly the way we thought it would. So it's going to go through the x-intercept here. It's going to go through that point, and it's going to wind up going out towards the horizontal asymptote. And that is how we work with test regions. So we have our 3 test regions, as you can see. And that is the behavior of the graph, and that's exactly the way you do it. That's exactly how you set it up. You start at negative infinity, and then you go to any, and you stop at any place that has a vertical asymptote or an x-intercept, and you create your test regions. And then you just pick x values in those regions, and that tells you whether the graph is going to behave above the x-axis or below the x-axis within those regions. And that's really it. So hopefully that all made sense. And what we're going to do in the very last part of this video is I'm just going to show you a more algebraic approach of determining whether a graph will go through a horizontal asymptote. All right, so we'll see you in the next section. In this section, we're going to determine a more algebraic approach of whether a rational function will actually intersect a horizontal asymptote. And before I get into the example that we worked on thus far in the video, I want to show you a more general approach to this occurrence. So if I took just a piece of a rational function, so if I took this part here, and let's say it intersected the horizontal asymptote right here, right? So we're not really sure what the x-coordinate would be. Let's say it would be negative x, comma, but we are sure of what the y-coordinate would be, right? Because on that line, every y-coordinate has to be 1. So if the graph is going to intersect the asymptote right on this line here, the y-coordinate is going to be 1. Which means that at some place, the function has to equal a y value of 1. We just need to figure out if there's an x-coordinate to go with that y-coordinate of 1. All right, so what we're going to do, I'm going to go to the original function now, and we know I have the original function already factored, and I have the factors canceled there. So the reduced function was f of x equals x minus 3 over x minus 1. And you want to do this with the reduced function, all right? And the horizontal asymptote of our function was y equals 1, if you can remember. And based on the logic in the explanation that I just did over here, if our reduced function is going to reach the horizontal asymptote of y equals 1, that means at some point the y-coordinate has to also equal 1, all right? And then all we're going to do is figure out if there's an x-coordinate to go with that. So we're going to substitute this in. So I'm going to substitute the 1 in for f of x minus 3 over x minus 1. And then we're just going to solve the equation. So to solve this, I need to remove the fraction. I'm going to multiply both sides by x minus 1. And now on the left side, all we're going to do is distribute this. So we're going to have x minus 1. And on the right side, we're going to cancel these factors, and we're left with x minus 3. And you can kind of see, if we solve this, you can kind of see what's going to happen here. These are the same sign. So when I combine my terms here, the x's are going to disappear, and I'm left with negative 1 equals negative 3. We know that's not true. So what we tried to do is we tried to see if there was an x-coordinate to match up with this y-coordinate of 1, and the equation failed. The solving part failed. So what that tells us is there is no x-coordinate where the y-coordinate is also equal to 1. So when this happens and the equation is not solvable, it's not going to cross, right? So it's not going to cross the horizontal asymptote. So that's really the test. That's your more algebraic approach. I mean, you could plot points and try to do it, brute force that way, but this is obviously a lot more efficient. What we're going to do on the next example is I'm going to show you one where it actually will cross. So I have this function here, f of x equals 3x squared plus 3x over x squared minus x minus 6. And again, you always want to try to factor this to see if we can cancel out any common factors. And I couldn't do that. So when you're doing this test to see if it'll cross the horizontal asymptote and you can't cancel any factors here, it's easier to work on the original. So that's what we're going to do. So the first thing you need to do is you need to figure out what your horizontal asymptote would be. And since both of the degrees for the numerator and the denominator are the same, you're going to look to the lead coefficient over the lead coefficient. So my horizontal asymptote would be, it's 3. All right. So what we're going to do is we're going to take this 3 and we're going to wind up substituting it right in here like we did in the other example on the other side and see if it works. So let's see what happens. I'm just going to move this up just a little bit. And we're going to have 3 equals 3x squared plus 3x over x squared minus x minus 6. And we're going to solve the equation. So on this side, I need to multiply by x squared minus x minus 6 to remove the fraction. And I'm going to do the same thing on the other side, x squared minus x minus 6. Now on the right side, these will cancel. And we're left with just 3x squared plus 3x. And on the left side, we're going to wind up distributing the 3 to everything inside there. So we have 3x squared minus 3x minus 18, and now we can solve this. So we're going to combine terms. We're going to subtract 3x on both, or 3x squared on both sides. That should be a square. The 3x squares will cancel, and I have negative 3x minus 18 equals 3x. And at this point, you can clearly see we're going to be able to solve this. All right, so there is going to be a place where this particular example would cross the horizontal asymptote. So let's finish this. So if I was to add 3x on both sides, I'm going to have negative 18 equals 6x. And then just moving this up just a little bit, we're going to divide by 6. And we're going to wind up getting x equals negative 3. So this function would actually cross the horizontal asymptote at the point. Now remember, this is my x-coordinate. This would be negative 3. And then my y-coordinate was right here. It would be 3. So with this case, in this particular, with this particular function example, we would have an instance where the graph is going to cross the horizontal asymptote. So hopefully that makes sense. That's really all you're going to do. First thing is you make sure you find your horizontal asymptote like I did over here at y equals 3. And then all we did was we took that 3 value and then just substituted into the function. All right, so if I get rid of this, we just substituted it back into the function and then we solved it. We went through all the steps to solve the equation. So hopefully that all makes sense, and what we're going to do is we're going to continue this series on graphing rational functions. We're going to come up with another example and work through all the steps as we've been doing it. So I'll see you in the next video. Take care.